In the fiery beginning of our young solar system, worlds are born and obliterated. Gas giants stir chaos, and a young sun vents its rage. How did Earth survive against all odds? Gazing down from space, we marvel at Earth's bountiful oceans, its continents, and life-giving atmosphere. We ask, how did our planet begin? How did it come to support life? And life to support Earth? The story of Earth starts within a giant spiral galaxy, the Milky Way. At 100,000 light-years across, the galaxy is a cauldron of swirling dust clouds and glowing gas. This simulated view shows a 50 million year span, a cosmological blink of an eye. In that time, millions of stars die in powerful explosions called supernovae, shown here as flashes of light. They seed the cosmos with the stuff of planets. Carbon, silicon, iron, and more. One explosion has packed enough punch to send a nearby cloud of stardust into collapse. Huge volumes of dust and gas stream into its core. This cloud is about as cold as the universe gets. But the tighter it's packed, the more it heats up. A storm erupts at its center, a vast, raging hurricane of dust, gas, and ice crystals. In its eye, temperatures soar. A star ignites, and our sun is born. The sun is being fed by a slowly spinning disk, the cradle of our solar system. Within the disk, planets take shape in a long and violent process. It starts with dust gathering into sand-like grains. They form pebble-sized objects within clouds of loose gravel. Over millions of years, gravity draws them together to form rocks, ice balls, and boulders. These objects coalesce into miniature planets or planetesimals. One such body, the primordial Earth, is growing steadily, but its fate hangs in the balance. We once thought that planet formation followed a predictable pattern. Our planetary neighbors bear this out with their nearly circular orbits. And the neat division between gaseous outer planets, Jupiter, Saturn, Uranus, and Neptune, and rocky inner planets, Mercury, Venus, Earth, and Mars. This division originates soon after a star ignites. The young sun produces hot winds that drive lighter hydrogen gas to the outer part of the disk. Beyond a point called the ice line, large gas planets grow quickly by sweeping up gas pushed out by the sun. The dusty inner region, devoid of gas and ice, is where rocky worlds like Earth form. This is not necessarily how most solar systems end up. A new generation of planet-finding telescopes has found that gas planets the size of our Neptune commonly patrol the inner zones. Jupiter-sized giants have been found orbiting so close to the star that hot stellar winds are stripping them of gas. Then there's a class of large rocky planets called super-Earths. How did those planets get there? Why did our own inner planets stay so small? Much of what we know about the formation of our solar system comes from asteroids that haven't changed since they formed almost 5 billion years ago. Most are so small that they simply burn up in our atmosphere. A few larger ones survived the fall. Scientists have been able to date these planetary shards by measuring molecular variations, called isotopes, in particular metals. They appear to come from two distinct asteroid populations that formed in the inner and the outer solar system. Something must have driven a wedge between these two regions, preventing the objects from mixing. If this great divider was the young Jupiter, it had to have grown quickly. It would have cut off the flow of matter into the inner solar system, stalling the formation of large rocky planets or super-Earths. Jupiter would then play a central role in one of the most impactful chapters in the history of our solar system. Scientists have used supercomputers to model Jupiter's rise by simulating the interaction of dust, gas, ice, and boulders in the early solar system. Each flash marks a collision. Each ring tracks the orbit of a would-be planet. Giant Jupiter forms on the periphery, its orbit shown in blue. As it grows, Jupiter succumbs to the gravitational pull of the inner solar system. It begins to spiral toward the Sun. Scientists call Jupiter's big move the Grand Tack, named for the turn a sailboat takes into the wind. Along the way, Jupiter plows through clouds of cosmic debris. What it doesn't swallow, it flings out of the solar system. The closer Jupiter draws toward the Sun, the more cosmic clutter it clears away. The simulation tracks Jupiter all the way in to the orbit of present-day Mars. Jupiter's Grand Tack has further reduced the mass of the inner solar system. Now, any planets that form there will be relatively small. In time, another giant planet, Saturn, grows large enough to pull Jupiter back out. Earth, at that time, would have been an embryo of the planet it would one day become. With Jupiter's departure, Earth and a few dozen hungry competitors are free to scour the inner solar system for scraps. Which ones will survive depends on the luck of the cosmic draw. Over the 50 million years since Jupiter departed the inner solar system, the roller derby of planets goes wild. As the remaining planets tug on one another, their orbits destabilize. Collisions between them are inevitable. What's left is a handful of would-be worlds, including the planets we know today, and at least one other. Its existence was deduced in the wake of one of the most celebrated milestones in the history of human exploration. On July the 16th, 1969, Apollo 11 blasts off. 13 launches, the US heavy-lift launch vehicle, the mighty Saturn V rocket, never failed to safely deliver its payload. Six times in the 4 years from 1969 to 1972, Apollo spacecraft drifted down over a pocked lunar surface. "12 astronauts climbed out to experience the moon up close. They set up experiments, made measurements, and collected rocks as they walked or drove across the alien terrain. The world cheered as the astronauts returned to Earth. Their exploits symbolized a spirit of optimism, a bright ray of hope in a troubled time. They were the first and so far the last humans to travel beyond Earth and land on another world. Few suspected at the time that the rocks they brought back to Earth would spur a chain of major discoveries about the Moon and Earth. Back in NASA labs, scientists found that rocks from the Moon have much in common with those from Earth. In particular, they share forms of oxygen regarded as blood types for solar system bodies. The two bodies share a common and violent history. That history is written across the lunar surface. The Moon is pocked with large old craters surrounded by concentric rings. You can see them in this image of the Mare Orientale, captured recently by NASA's Lunar Reconnaissance Orbiter. The rings suggest that a giant impactor came down on a roiling red-hot liquid surface, sending ripples outward. The astronauts encountered relatively light rocks strewn about the landing sites, probably forced to the surface by heavier material as it sunk down into the magma. They also picked up rocks eventually nicknamed creep for the constituents: potassium, rare earth elements, and phosphorus. These rocks, of a type called anorthosite, are a product of a molten surface. What had turned the Moon into an ocean of molten rock? And what is the connection to Earth? The most widely accepted theory takes us back to a time 4.5 billion years ago. At this time, Earth may harbor volcanoes on its surface with a thin, toxic atmosphere. Our planet has so far withstood the onslaught of planet formation. It now awaits the test of its life. Another planet, about half its size, is closing in. This is Theia, a world that might have been. Instead, its journey ends here, as it bears down on Earth. Imagine the view from Earth as the ultimate threat looms large on the horizon. Theia rocks Earth to the core. The impact shears away a third of our planet. But instead of destroying Earth, Theia becomes part of it. A computer simulation captures the first 24 hours. Debris unleashed by the collision envelops Earth in a dense atmosphere of vaporized rock. The cloud coalesces into a ring, a belt of molten rubble. Much of the orbiting debris rains back to the surface. But within a century, what's left gathers into a single wondrous body. Earth's companion, the Moon. After the impact, our planet is left spinning rapidly on a slightly tilted axis. The Moon orbits much closer to Earth than it does today. From its surface, our world would have filled the sky. As the Moon gradually slips into a more distant orbit, it exerts a drag on Earth. That slows our planet's spin and steadies its tilt. The Moon serves as a reminder of the cataclysm that almost spelled the end of our planet. But from here on, it would be a welcome constant, a source of stability, and ultimately, beauty. But the violence was by no means over. Unlike Earth, where erosion and geological events have erased all traces of the distant past, the Moon holds a record of the battering that followed. The myriad craters that line the lunar surface tell of a time up to 4 billion years ago, when Jupiter and Saturn hurled a barrage of objects toward the inner solar system. A recent study draws on the sizes and number of lunar craters to model the impacts endured by Earth. At least 4 impacts would have been large enough to remake the surface of our planet and to radically alter the course of its history. Smashing into a crust rich in radioactive uranium and potassium, they tore these elements from the planet and sent them into space. This process, called impact erosion, left a crust that would cool more quickly when the impacts finally died down. Less disruptive impacts are thought to have carried in massive amounts of water or released water bound to minerals deep below the surface. Half a billion years after the birth of the Moon, Earth has become a world of water. Its seas span every horizon, broken only by volcanic islands. The Moon, still in close orbit, whips up tides that lash rocky volcanic shores. Earth's atmosphere is a mix of hydrogen, nitrogen, and carbon dioxide, laced with water vapor. Land and sea are rich with chemicals, carbon, nitrogen, oxygen, iron, and more that came with the dawn of the solar system. The Earth has what it needs to accomplish its ultimate feat, to nurture life. But there's a problem. Its water is slowly disappearing. The young sun, while dimmer than it is today, is prone to powerful flares. They strike the Earth's upper atmosphere. When a solar particle hits a water molecule, H2O, it can blast it apart. Lightweight hydrogen wafts into space, while heavier oxygen sinks to the surface and binds with rocks. We now know what a devastating effect this can have. Spacecraft observations show that Mars long ago harbored ample stores of water. Its surface is etched by the meandering paths of ancient rivers and lined with sediments laid down on lake and ocean beds. Mars today is a lifeless world, graced with a thin carbon dioxide atmosphere. There is little or no water left. Using special sensors, orbiting spacecraft have documented the ongoing loss of water in Mars's upper atmosphere, stripped by solar radiation. Scientists have observed this same process at work on Earth's sister planet, Venus. The result, Venus's atmosphere today is a witch's brew of noxious chemicals, including thick, sulfurous clouds. Down at the surface, Venus's atmosphere is choked with high concentrations of carbon dioxide, a potent greenhouse gas that traps the sun's heat. CO2 has turned Venus into a cauldron. With surface temperatures of almost 500 degrees Celsius, Venus is the hottest planet in the solar system. This hostile environment is reinforced by active volcanoes that dot its surface, spewing sulfur and carbon dioxide. How did Earth avoid such a grim fate? For one, our planet has a protective shield that both Venus and Mars lack. It's a magnetic field that deflects the most powerful waves of radiation the sun can throw at us. Generated by the exchange of heat between Earth's core and its crust, this magnetic field is a legacy of rapid surface cooling early in the planet's history. It's just our first line of defense. Another line of defense began to simmer away across the surface of our planet as early as 4 billion years ago. Life. Long-standing theories see life's crucible in the stirrings of undersea volcanic vents. Heat and chemical reactions over long periods of time produced proteins and nucleic acids. The chemistry of life. More recent ideas point to hot springs and other volcanic features that dotted the landmasses of early Earth. No one knows exactly how or where life gained its first foothold. What we know is that it did emerge, and that it spread thanks to a key breakthrough. The ability to turn sunlight into energy. Photosynthesis, the process that fuels plant life, made its first appearance in simple bacteria over 3 billion years ago. Using one of the world's most powerful supercomputers, scientists have sought to model its chemical secrets. Step 1 is to capture sunlight. Passing through a transparent membrane to the center of the bacteria, we encounter a cluster of spherical pods. Each one is equipped with special sensors designed to harvest solar energy. When a photon hits, it excites rings of chlorophyll molecules. This energy is transferred across a family of proteins, the machines of life. Down the line, electrons and protons carry the energy through a chain of chemical reactions. The energy driving these reactions came from the sun. The cell must now convert it into action. It's the energy stored in protons that gets things moving. Streaming into watery spaces within the cell, they flow toward a towering molecular structure. As they enter, their electrical charges turn a protein like a crank. This turning motion initiates a chemical reaction, one that is essential to all life on Earth. Two molecules join to form a third, called ATP, shown in blue. It is the universal energy currency in every cell that has ever lived. Like a biological battery, ATP stores energy captured from the sun, repackaged in a stable form that the cell can now use to break down food, to power locomotion, to fuel reproduction, to live. ATP made it possible for microorganisms to flourish and evolve. As bacteria gave rise to plants, a more advanced form of photosynthesis released a byproduct: oxygen. This new supply of free oxygen surpassed the amount absorbed by the land and the oceans. In the atmosphere, it bound with hydrogen, preventing its escape into space while forming a new molecule of water. This process will gradually stem the loss of Earth's oceans, though not completely. A recent study concluded that our planet has still lost up to 25% of its original stores of water. Across the surface of our planet, water began to work in tandem with life, the sun, and geology, to power a remarkable planetary engine: the climate. The climate is driven in part by the unevenness of solar heating due to the cycles of day and night and the seasons. These factors moderate global temperatures, sending warm tropical winds toward the poles and cold polar air toward the equator. tides and currents mix cold water from the deep with the warm surface. Solar energy is trapped in the atmosphere by water vapor, along with carbon dioxide, the greenhouse gas that ruined Venus. What keeps CO2 in check is the special ingredient that sets Earth apart: life. The oceans are chock full of it. Microscopic phytoplankton take in CO2, driven into the ocean by waves or drawn up from the deep by currents. They send the carbon atoms on a journey up the food chain. Phytoplankton get eaten by zooplankton, like these radiolarians, a creature that dates back to a time over 500 million years ago when life exploded across Earth's oceans. Moving up in scale, copepods are tiny bug-like crustaceans and the single largest source of protein in the sea. Octopus larvae are part of a vast zoo of creatures smaller than the tip of your finger. They get eaten by small fish, and they in turn by larger creatures. At each step in the food chain, the carbon that began as part of a diffuse gas in the air is passed on to larger and larger animals. The larger the body, the greater the mass of carbon. From whales down to tiny phytoplankton, marine life is part of a global system of removing CO2 from the atmosphere, then gradually releasing it back. The key to this carbon cycle is Earth's ability to store it long term. A NASA satellite is tuned to read chlorophyll, a chemical tracer for plant growth. In sync with the seasons, plants take in vast amounts of carbon dioxide while releasing the oxygen we breathe. On land, carbon finds its way into the ground when plants and animals die and decay. The Earth too gets into the act. Exposed rocks take in CO2 when it rains. Erosion sends it into the oceans. If it becomes part of the marine food chain, carbon-rich matter can sink all the way to the sea bottom in the form of waste. In time, carbon-rich sediments can turn to oil or to rock like limestone. Carbon can return to the environment if rocks become exposed or if the Earth begins to erupt. Every year, over 100 million tons of carbon dioxide are spewed into the oceans and atmosphere by volcanoes. Acting on timescales of a day to millions of years, the carbon cycle has helped to make our planet habitable. Its success depends on life itself. Earth today, endowed with ocean, atmosphere and land, with light and warmth, with life that's bountiful and in balance. As we study the intricacies of what makes our planet tick, we marvel at what it took to achieve all that. The aftershocks of a supernova. The violence of Jupiter. A chance collision. And the gift of a moon. Of water and life. The more we're able to reconstruct our planet's past, the more singular it seems. That is, until we realize how many other solar systems are out there. We ask, is Earth just one of countless habitable worlds in a galaxy bursting with life? Or is it a wondrous twist of fate? A remarkable convergence of chemistry, energy, and chance? Our planet became a paradise. But is it the only one?